Thank you very much for having me. I want to thank the organizers also for the opportunity to tell you guys about the kinds of systems that I'm building up in my laboratory at the University of Maryland. And so my group is a circuit QED group. And so one of our basic building blocks is the microwave resonator. And this is a schematic of our favorite one. It's the coplanar waveguide resonator. And so what you should think of this as is a two-dimensional analog of a coaxial cable. So there's a central conductor and then two ground planes on either side. And this forms a very high quality 1D waveguide for microwave photons. And then if you cut the center pin in two places, then you form an impedance mismatch, which acts like a mirror, and it bounces the microwave photons back and forth, and they follow the center pin, and it forms this very high quality one-dimensional cavity for microwave photons. So this is a schematic. In practice, they look a little bit more like this. So they're fairly large by fabrication standards. And so we tend to fabricate them with these extra meanders in them to compactify them. And the fact that we can put these meanders in is actually going to be key to some of the stuff I tell you later on. But at the very high level, if you don't want to think about what this actually looks like in a circuit, it is just a harmonic oscillator. Instead of position and momentum, it's the charge and the flux on an effective inductor and capacitor. But so this is basically going to be my favorite harmonic oscillator for the talk. And then in addition to this harmonic oscillator, obviously we can also incorporate superconducting qubits. And so this is now a circuit schematic of the current most common variety, the Transmon qubit. And so what it is a capacitor in parallel with a Josephson junction. This particular one has a squid instead of a Josephson junction, which just allows you to tune the Josephson energy. But again, at a very high level, what this is an n-harmonic oscillator. So instead of n squared phi squared that would give you a harmonic oscillator, this is cosine phi. And so it has higher order terms that make this a nonlinear oscillator. And the Transmon regime of this circuit is where the EJ coefficient is the largest. And so actually the way that we like to think about this is actually as a particle in a cosinusoidal well. And so the fact that it's a cosine well instead of a parabolic well means that the bound states of the potential are not equally spaced. And so if we are sufficiently careful not to drive too fast or too hard, we can isolate these lowest two levels to form an artificial two-level system. And that's really the Transmon qubit. And so we can fabricate this inside of a cavity, and then we get a model that has showed up, I think, quite a few times at this meeting so far. So we get Jane's Cummings. So we have a harmonic oscillator description of the cavity, an effective two-level description of the qubit, and then the native interaction between them is just dipolar energy exchange, where one excites, the other de-excites, and they trade the excitation between them. And so this is our basic single cavity building block. And so what this is naturally tending to build are photon mediated spin interactions when you put multiple qubits into a cavity or you start wiring these things up. And so what my group really focuses on is what regimes can we get into if instead of looking at a single mode cavity, we start to look at multi-mode structures. And in particular, if we start to think about what happens when you put qubits into a photonic crystal. And so if you put two qubits into a single cavity, as I said, the native interaction is going to be a swap, where basically one qubit de-excites, emits into the cavity, and then that photon is absorbed by the other one. And so you get this sigma minus, sigma plus swap interaction. And now if you do this in a photonic crystal, then you get that swap interaction actually in all of the modes in parallel. And each of the cavity modes has a possibly different coupling, a possibly different detuning, and really crucially, they have different mode functions. And so the position dependence of the mode function causes interference. And so when you do this in a photonic crystal, you get an envelope that comes from what the crystal mode structure looks like. And in a 1D chain, what you natively get is an exponentially localized interaction or an exponentially localized photonic bound state. And this has been well known. It's been measured in a few different groups now. This is data from the Hauk lab in, I think, 2019 or so. And so what my group is focusing on is to go beyond this relatively simple exponentially localized interaction in 1D and to go to new regimes. And so there are two ways that you can take this basic mechanism and get different interactions. So the first is to take it to different lattices. And the second is to change the coupling scheme to something more versatile that gives you a little bit more degrees of freedom. And so I'm going to start by telling you about the kinds of lattices that we have access to with coplanar waveguides and the kinds of interactions that they sort of natively allow us to build. And then at the end of my talk, I'll tell you a bit about some things that we're working on to go to a new coupling scheme. Okay, and so finally, this is actually a picture of what a photonic crystal looks like for me. So this was a device made in the Hauck lab a few years ago now. And so each one of these squiggly lines here is a coplanar waveguide resonator, and they meet at these little black dots. And so if we zoom in on one of these regions, then this is what's going on with the different cavities. So this is the center pins of 3 different cavities are converging on this one spot, and then they flare out a little bit. And so in this region, there's an enhanced capacitance between the center pins of the different cavities. And this allows a microwave photon that's rattling around in this cavity to hop over to either that one or that one. And so we have this capacitively coupled resonator network. And we really like to think of it as a tight binding solid for photons. So the resonator frequency sets the on-site energy, and then there are hopping terms given by who is connected to whom by these capacitors. One minor thing that I want to point out is that the sign of the hopping is unusual. There's a few too many minus signs in this equation, but basically the upshot is that normally you expect the ground state of a system to have a slowly varying wave function and excited states to have rapidly oscillating wave functions. And for us, that's reversed. Things with a high phase gradient are actually the low energy states, and the uniform state or the constant function is actually going to be the highest excited state. But this is just a global minus sign on what you would expect, say, in electronic band structures. In addition to this slightly incidental minus sign, there are really 2 key properties of these resonator lattices that allow us to go to new lattices. And so the first one is that this lattice site is in a certain sense deformable. And so what do I mean by that? So let's take a look. This is the CAD design for one of these resonators. And so, as I said, photons in here, they propagate along the waveguide and then bounce back from the ends. And so the resonance frequency is set by having constructive interference when you do that bounce back. And so the frequency depends on the total arc length of the waveguide. And crucially, however, all of the hopping, all of the coupling comes from end. It doesn't have anything to do with what's going on in the middle of the resonator. It really comes from ends. And so when you combine the fact that we can meander this resonator in different ways, it means that you can take the same resonator and realize it in a bunch of different shapes. And so these 3 resonators, or these 3 CAD designs, they look very different at the hardware level to us from the outside, but from the point of view of a microwave photon traveling inside this circuit, these can be completely identical lattice sites with the same resonance frequency and the same connectivity. And so there's a native decoupling between distance and geometry on the chip where we actually realize the device, and the distance and the geometry that is felt by the microwave photons propagating in the device. And so one of the things that this allows us to do is we can actually realize lattices where the photons feel an effective curvature. And so this is a photograph of the device that we made when I was a postdoc with Andrew Hauck. And so this is a lattice where the microwave photons propagate as if they were moving in an effective space with negative hyperbolic curvature. So what is this thing? So I've put next to the device itself a couple of graphs to try to help make it clear what's going on here. And so this graph shows the connectivity of the device. And so if you look at the center of the device, we see there's a ring of 7 resonators. And so they're each on top of these dark blue edges of this central heptagon here. And then if you go a little bit to the side, then this is another 7-sided ring. And so that's here, 1, 2, 3, 4, 5, 6, 7. And so these resonators are actually laid out on a hyperbolic version of the honeycomb lattice that instead of having hexagonal plaquettes, it has heptagonal plaquettes. And so this particular sketch shows the actual device geometry, and this is a more visually pleasing conformal drawing of the infinite version of the lattice that this is a piece of. And then down here at the bottom, we have experimental verification that we're able to do the microwave engineering of this device sufficiently well that the pretty story I told you on the previous slide is actually true. So in blue, we have experimental transmission taken by sending microwave photons in through one of these antennae and out the other. And then in red, we have theoretical transmission for a few different disorder realizations. And so we can see that sort of the variations between the disorder largely account for the difference between a given disorder curve and the theory. And so we are actually able to do this. And this is what we showed when I was a postdoc. And now at this point, you're probably wondering why I'm showing pictures that have not only this hyperbolic honeycomb lattice shown in light blue here, but also a hyperbolic kagome-like lattice drawn on top. So this is the light blue in the background here and the dark blue in the background there. And so the reason that I'm showing you the kagome is that in fact, that's actually the lattice that is being realized here. And this is because our lattice sites very unusually are not point-like objects, they are one-dimensional objects. And so if we zoom in on a lattice device, now let's look at a Euclidean one for simplicity, and we try to see what sort of lattice is going on here, then your eye probably picked out this honeycomb lattice that I've highlighted. But I have lied to you, because what I have done is I've implicitly put the lattice sites on the coupling capacitors and the hopping matrix elements along each of the resonators. And so this describes my hardware connectivity, but it does not describe how photons propagate in this device. Photons move instead on the kagome lattice, because this has a lattice site on every resonator, and two resonators share a hopping matrix element if their ends touch. And so naturally, when we make these devices, there are sort of two lattices that show up, one that I will call the layout lattice, which is the one that's easy to see and describes in general the hardware connectivity, but the effective lattice for photons is always going to be this kagome-like object. And this is actually a mathematical object called a line graph, and they have very special properties. And so every lattice that we make is going to be of this line graph type. And so let's have a look at what that actually means. And so I like to look at a couple of examples. So probably the most common example of a graph and its line graph is graphene. So here's graphene and its band structure. And as I said, its line graph is the kagome lattice. And this is the band structure of the kagome lattice. For the experts here, this is for our sign of the hopping. And so it's upside down from standard. And we can also look at another canonical example being the square lattice. Its line graph looks like this. It's a little bit more complicated. If somebody asks me afterwards, I can explain why this is the right graph. But the key is really to compare these band structures with these over here. And we see that there's a pattern, that each of these line graphs has a flat band at -2. And then the dispersive bands that show up, they look identical to the bands of the original lattice. And this is actually not an accident. It turns out this is a very general graph theoretic fact about regular graphs. And so if you start from a lattice where every site has the same number of neighbors and you take the line graph, then this is always what you get, that you get two types of eigenvalues on the line graph. You get shifted bands of the original, and you get the flat bands at -2. And so knowing this, we can actually use some graph theory tricks. I think I'll speed up a little bit to make an example where this flat band is by itself. And so we start from graphene. We're going to take a detour through this particular lattice where we add a new lattice site in the middle of every edge. And then we will take the line graph of that. And so what we obtain is this example here. And now if you look at it like graphene that it came from, everything has 3 neighbors. And so this is actually very easy for us to use as a hardware layout. But if you compute the band structure, it has no states below -2. And so when you use this for the layout, the line graph, the effective model for the photons looks like this. And it has a flat band at -2 with a very, very, very large gap. In fact, the largest possible gap. And so putting that all together, we have these 2 unique properties, namely this deformability and this sort of innate tendency to form flat bands. And each of these leads to interesting photon mediated spin models. So if you put qubits into this hyperbolic lattice, we were able to show in a preprint that should be appearing hopefully any day now, that the photon mediated spin-spin interactions inherit the hyperbolic structure of the lattice that they're in. And so you get a hyperbolically connected photon mediated spin model. If we look at the line graph flat bands, so for example, from this lattice, the flat band itself consists entirely of oscillatory solutions. And so in this lattice, you can couple to the flat band alone, and that actually gives rise to a short range frustrated magnet. And so this is sort of the one direction that we're going in, is really exploiting the native hardware capability to get to these new kinds of lattices. And then in a lightning fast couple of minutes at the end, I think I will tell you about the other direction that we're going, which is to use a more sophisticated coupling scheme that gives us more flexibility. And so the idea is that instead of directly coupling the spin to the photons, we want to use a Raman transition. And so we'll do a transition in the qubit by combining a microwave drive and a cavity photon. And the crucial thing about this is that you get the same kind of effective swap interaction, but there are now 2 relevant detunings, the detuning to the intermediate state and the detuning to Raman resonance. And this gives you more control. And so if you have a 1D photonic crystal and a single drive, you again get an exponentially localized interaction. This was known for a long time. But the crucial difference is that it's easy to superimpose multiple drive frequencies. And when you do that, you can actually just add the interactions formed by the individual drives. And so you can build up new interactions sort of in the sense of a Laplace transform. And even in 1D, you can get an approximate power law interaction. The crucial difference is that you need now a 3-level qubit, which the Transmon very much is not. And so we have to go to flexonium instead. And so this is the circuit for flexonium. I'm running short on time, so I'll skip to the key point. So what flexonium is a cosinusoidal potential inside a quadratic well. So it has this sort of ripple structure, and it gives you 2 kinds of transitions. You can have intra-well transitions and inter-well transitions. And this gives you the sort of lambda or triangle structure that you need. And so we actually performed a proof of principle experiment to drive this cavity mediated Raman transition. And so the idea here is that we will put a pulse on one leg and rely on the vacuum Rabi coupling with the cavity to complete the transition. And so basically we pulse 1/2 of the lambda transition, and then we check whether we have depleted the G2 state. And so we found that indeed, if we hit the right frequency with the right power, then we can go from being always in the G1 state to flipping over to the G2 state. And if we drive harder and harder, we can do more and more oscillations. And so this was just to show that we could do this vacuum Rabi mediated Raman transition in a single flexonium. And what we're working on now is a newer device that's more optimized for seeing this. So it has a separate coupling cavity and readout resonators. Looks a little bit more complicated than the original, just to prove that we're experimentalists. And this is a photograph of an actual device. We're exploring this in the fridge right now and updating devices. And so with that, I'll just wrap up and say that we're very excited to develop this toolbox for making new and exciting forms of spin-spin interactions. And we have, as I said, these broadly 2 knobs that we have exciting lattices that we can make that are sort of unique to these coplanar waveguide lattices. And then we're also working on these Raman coupling schemes that give us active control over the spin-spin interactions. And I will just wrap up by thanking everyone that was involved in this particular project, in particular my postdoc advisor, Andrew Hauk, Alexei Gorshkov, who has been a major theory collaborator on this. Peter Sarnak is actually the mathematician who helped us figure out all of these graph theory tricks and the relations between graphs and line graphs, and then the students and postdocs involved in this work. Thank you.